Okay, so what we get to do right now is take the octet stability and apply it to understanding bonding. And I don't know, I think it's great how we can see we go from electron configuration to we get octet stability, and then we go to bonding. In fact, we can go to other things like bond angle and structures. So we can loop back to earlier in the course when we saw some crystal structures. It's all piecing together nicely. It's beautiful. I hope you'll agree with me. Okay, so let's take a look at this, and I want to cover the primary bonds. And first thing I want to do is cover the ionic bond. Okay, and so the ionic bond occurs in two logical steps, if you will, two logical steps. The first step is achieving low energy or a stable octet. And then the second logical step is the bond itself, really, which is the charge attraction. Okay, and I think the best way to illustrate this is with an example, and why not an example that we've already got a bit of knowledge of, sodium chloride. So neutral sodium has an atomic number of 11. So the electron configuration is 1s2, 2s2, 2p6, 3s1. And we look at that and we say that's irritating. Why is it irritating? Because it's just got this one pesky electron that is keeping it from having octet stability, 2s2, 2p6. Chlorine, on the other hand, is sitting here with atomic number 17. So it's 1s2, 2s2, 2p6, 3s2, 3p6. Correction. Whoops, I got ahead of myself. I got excited. 3p5, isn't it? Right? So that's 10 up till there. Plus 2 plus 5 is 17. And again, that's irritating. Why is that irritating? Because it's just one pesky electron away from, it's one electron deficient. Okay? Away from the octet stability. Now on their own, you know, chlorine can't just create an electron, and sodium can't just give up its electron on its own. But if you bring them together, we can have a transfer of electrons. And that's what this first step really is. If I complete this, it's achieving low energy by electron transfer. Okay, so electron transfer is really an important part of the ionic bond. And what happens then after that is this. We then have Na plus, it's lost an electron, so it's got a net positive charge, and we have chlorine minus, it's accepted an electron to achieve octet stability, and then there's a charge attraction between them. This charge attraction, and the charge attraction is the ionic bond. And let me illustrate that with a structure, well, the structure that we actually already know to be true for rock salt, for sodium chloride. It looks like this, doesn't it? That's an accurate two-dimensional slice through sodium chloride, where these are all the positive cations, and these blue ones are the negative anions. So the important thing to appreciate here is that the ionic bond is this general attraction between all oppositely charged ions. And you remember that there's one out in front of the page and one behind in this specific case, coordination number of 6. But this cation here is also attracted, although much more weakly, to these other anions out further distance away. So the bond itself, the charge attraction, or if you want to be fancy, you could call it a Coulombic attraction, is not depleted by the presence of other ions. And so it's for that reason that we say the ionic bond is non-directional. Okay? It's not between specific nuclei. It's between this one and all the other ones. It's like a bad analogy perhaps, but cool kid at the party, everybody wants to hang out with her or him, right? And there's a general attraction, right? And then you get married, and that's the covalent bond. Okay, and trust me, it's beautiful. All right, so with that, let's discuss the covalent bond. So the covalent bond now is achieved through an electron sharing. Okay, let's erase that. Electron sharing. Again, why? To achieve octet stability or low energy configuration. All right, and again, I think the best way to do this is by way of an example. And so let's look at methane, CH4. So carbon brings to the table 6 electrons, 1s2, 2s2, 2p2, and hydrogen brings to the table just 1. So how are we going to do this? How are we going to rationalize this? Well, if we take carbon like this with its 4 electrons, and then let's say today I make hydrogen, it's going to be red, and it has 1 electron. Well, if 1 carbon gets together with 4 hydrogens, then carbon has 8 electrons and hydrogen has its 2. And remember, we give hydrogen a pass because it can look like helium. So that's kind of duet stability, if you will. Hydrogen has no higher ambition in life than to look like helium. Everything else wants to have octet stability. I wanted to just mention briefly here that I did something in this little depiction that I should probably explain. And it's actually really interesting. You know, perhaps you've even seen methane depicted like this. When we covered polymers, I did all these little lines without explaining what they were. Now you know they're the covalent bond. But how did I make 4 equivalent bonds? There's 4, and they're all equivalent. They're all the same. In fact, if you saw that structure, it would be this tetrahedral structure. And the way that's achieved is really neat. Okay, we've got, because you'll take a look at this electron configuration that carbon has. It's got the s electrons, and then it's got p. It's got 2s, and it's got 2p. And different energy levels. So how on earth are we going to form 4 bonds that are equivalent with electrons having different energy? And the trick is this. We say, what if we just take them, put them all together, mix them up, make a blend, make a hybrid, right? What if we make a hybrid shell, hybrid, whoops, let's put my B, okay, hybrid, there we go, that's spelled correctly now, hybrid, and we just blended them all together so we have 4. And we did that by combining 1 S and 3 P's. We could call it sp3, and in fact we'd call it sp3 hybridization. So that's the way that carbon bonds, and we'll look at that a little later when we talk about the structure of diamond, which is also sp3 hybridized. Okay, fantastic. We're motoring along here, doing really well, and we're going to look now at the metallic bond. Okay, the metallic bond. Now we're going to treat this twice. First time we're going to look at it with a kind of a basic model, and then we're going to dive in a bit deeper and have the so-called band theory of solids, which is a more detailed look at it. But for now, we're going to just look at this, the sea of electron model, and it's this, that the valence electrons are contributed to a sea of electrons. What does that mean? Well, that means that you take all these atoms, and we've seen these with our crystal structures. Now we have a new appreciation for what we were looking at. But these are actually just the nuclei plus the core electrons. Okay, and you'll see. So it's the nucleus plus the core electrons, non-valence electrons. Okay. And what happened to their electrons? Well, their electrons went into this, let's see if I can sketch it like this, into this sea of electrons. They're just sort of free to move around. They're delocalized. And there's like the glue holding this whole thing together. Okay? So this is the sea, as it's called when we're discussing this model, of electrons. And this is actually, it's not too bad. It's not entirely correct, but it's not bad. If you apply a voltage across this, you can get movement, conduction of electricity. That's explained through this. You can have cleavage of planes past one another all the time, being held together by the sea of electrons. So it's not a bad model, but we're going to see there's some insufficiencies in it, and that's one of the next things we need to do, is build this more detailed knowledge of the electron structure in solids. All right? Thanks so much.